it's Shannon Matrick-Myers, and today we'll be checking out basis and dimension of Rn. So here we go. Let's warm it up a little bit, do our math stretches. So if possible, write this vector z equal to -4, -3, 3. Remember, it terminates at that point as a linear combination of the vectors in the set S that terminate at 1, 2, -2, and 2, -1, 1. So, okay, let's see what we've got going on. So recall that a linear combination, and you want to just kind of get this in your brain, is the sum of scalar multiples that's in some set. So if we call this guy V1 and V2, then we would have C1 times V1 plus C2 times V2, and those two are equal to Z. So what was Z? -4, -3, 3 equal to C1 times V1, 1, 2, -2, plus C2 times V2, which was 2, -1, and 1. And just to show where we got everything, that was our Z, and then our V1 was this vector here, and our V2 was that last vector there. Groovy? All right, so let's check it out. Remember, you might, have caught on that you can go a little faster on this, but I'll continue since it's somewhat new to you still. Here, this could be what? C1, 2C1, -2C1, plus 2C2, -C2, and C2. All I did was bring the scalars C1 and C2 into their vectors. So, getting one happy vector on the right-hand side, we will have C1 plus 2C2, comma, 2C1 minus C2, comma, -2C1 plus C2. Groovy? Now, using the definition of vector equality, we will equate the components on the right side to their corresponding components on the left side. So that gives us the system C1 plus 2C2 is equal to -4. 2C1 minus C2 is equal to -3. And what do we get here? -2 C1 plus C2 is equal to 3. Cool so far? All right, well, let's put this in the form into the corresponding augmented matrix. We'll have 1, 1, -4, 2, -1, -3, and then -2, 1, and 3. And why don't you take a moment and, either using technology or by hand, go ahead and find the reduced row echelon form of this matrix. And we've got to enter our matrix in. So I did a bunch of screenshots for you in an earlier video, so you may want to check that out. I'll go ahead and go a little more quickly now. So second x inverse, and I want to edit matrix A. I have a 3x3 matrix, and when I enter in the numbers, I'll have 1, 2, -4, 2, -1, -3, and then -2, 1, and 3. So quitting out of the matrix, I go back into the matrix menu, and then I go to math, and my RREF is down here. And then I have to go second matrix and then decide which one I'm doing the math on. So that's our matrix A. So when we do this, we get the following matrix. So I will just go ahead and write that on R. So the RREF format is 1, 0, -2, 0, 1, -1, and then we have all zeros. Cool, cool. All right. What did we find out? Is it true? Is it not true? Well, let's put it back into terms of a system. So this gives us, remember we're doing the coefficients, so C1 is equal to -2, and C2 is equal to -1. Okay, so rewriting what we came up with, we would have -4, -3, and 3 is equal to -2. That's our C1 times 1, 2, -2 minus 1 times 2, -1, 1. So it works out just great. And you can kind of check that in your head, and you'll see that when you do the computations on the right side, you get the vector on the left side. So the answer is yes. Cool, cool? All right. Definition of linear combination of vectors in a vector space. So a vector V in a vector space, capital V, is called a linear combination of the vectors. Now this is a set of vectors, vector U1, vector U2, all the way down to vector UK in the space V, when the vector V can be written in the form V equals to C1 times U1 plus C2 times U2 plus ... plus CK UK. Cool, cool? Where C1, C2 down to CK are scalars, and scalars means they belong to the real numbers. Groovy? All right, so next up we have definition of a spanning set of a vector space. So if we have some set S equal to vector V1, vector V2, all the way down to vector VK, and this set S is a subset of some other vector space V. The set S is called a spanning set of the vector space V when every vector in the space V can be written as a linear combination of vectors in S. Cool, cool? All right, well, the first set S that we're looking at is just what you're used to, your I, J, and K. All right. Okay, so I've had each tick mark have a value of a half. Okay, so these are all tick marks in here, but I want to make it bigger so you can see everything. And then picturing this, it's always good to make a picture of what we're doing. So I'll do the first vector, the I vector in purple. 1, 0, 0 is here. And then continuing, we'll have 0, 1, 0 next. And that one goes along the y-axis. And then for our K vector, it'll look like this. Groovy? So that is the picture of our set S of vectors. Good so far? Awesome. And actually I can label these. This is 0, 0, 1. And then we could call this V3, right? If we want to. And then this one would be 0, 1, 0. And we could call this one V2. And in the purple we had our V1 equal to 1, 0, 0. Cool, cool? So, all right, let's think about, do you think this one would span? We need to figure out if we can utilize these three vectors in a linear combination to get any vector in R3. Groovy? So let's check it out. Let's let U equal to U1, U2, and U3 be any vector in R3. So that would just mean what? That I would belong to the set of real numbers such that I equals 1, 2, and 3. Groovy? Okay, what do we do? How do we make a linear combination? I mean, this is going back to the problem we just did as our warm-up. We want to be able to write U as a linear combination of the vectors v1, 2, and 3. So we would have C1 times V1 plus C2 times V2 plus C3 times V3, the vector V3. Good so far? All right, well, what is U? Beautiful. U is U1, U2, U3 in component form. And we need to write this as C1 times 1, 0, 0, because that was vector V1, plus C2 times 0, 1, 0, plus C3 times 0, 0, 1. Good so far? All right, so if we were to, highlight corresponding vectors, this one here would be our V2, our V3 is the 0, 1, 1, and then our V1 is 1, 0, 0. Okay, so, well, what are we going to have here? Again, we'll still show all the work here. Do you see that you'd have C1, 0, 0 plus 0, C2, 0 plus 0, 0, C3 once you brought those scalars in. And then getting them in terms of one happy vector, what would we have? We'd have C1 plus 0, C1. So we would just have C1, C2, C3. Well, this is one of those so easy it's hard things, right? Because when you equate the, components in the right side to their corresponding components in the left side, what would happen? We would just have C1 is U1, C2 is U2, and C3 is U3. And so what does that mean? Well, that means that we can write U as u1 times 1, 0, 0 plus u2 times 0, 1, 0 plus u3 times 0, 0, 1. Cool so far? Well, that leaves it pretty open, right? Because don't u1, u2, and u3 belong to the real numbers? So, therefore, the set S equal to 1, 0, 0, 0, 1, 0, 0, 0, 1 spans R3. Cool, cool? So you can get any single vector in R3 by using a linear combination of these three vectors, 1, 0, 0, 0, 1, 0, and 0, 0, 1. Super powerful stuff. Cool, cool? What about this next one? Well, we have S is 1, 2, 3, 0, 1, 2, negative 1, 1, 1, those three vectors. All right, so let's just use the same colors as before. So our very first vector would be, I'll make this bigger while I'm drawing it. We have, 1, 2, 3. Okay, so it'll go about here. And then I can erase these guides. And then our next one will be this pink color, so 0, 1, 2. All right, so we'll be here for our 1. Alrighty, and then we'll have the last one in the blue, and the last one was negative 1, 1, 1. So X will start back here, and then, so negative 1, 1 takes us here. And then do you see it's kind of weird because this is the 1 value for the z-axis, and it traces over right where we plotted that point. So it's kind of a funky one from this view, but will be looking like this. And again, we've got this is our V3. So V3 was equal to negative 1, 1, 1. And call this one V2, and that was equal to 0, 1, 2. And then V1 was equal to 1, 2, 3. Cool, cool? All right, I like for you guys to see where things come from. Okay, so now let's start figuring out this problem. All right, so again, why don't we let U equal to U1, U2, U3 such that UI belongs to the real numbers for I equal 1, 2, and 3. And what will we have? We'll have U equals C1 V1 plus C2 V2 plus C3 V3. And then plugging in what we know, U is U1, U2, and U3 as component form, or in component form. And then we'll have C1 times 1, 2, 3 plus C2 times 0, 1, 2 plus C3 times negative 1, 1, and 1. Good so far? Writing our linear combination, all right, so we would have U1, U2, U3 equal to C1, 2C1, 3C1 plus 0C2, 2C2 plus negative C3, C3, C3. Groovy? Awesome. And then what? Very good. Make them one happy vector. So we'll have U1, U2, U3 equals to C1 minus C3, comma, 2C1 plus C2 plus C3, and then finally 3C1, 2C2 plus 2C2 plus C3. Groovy? Awesomely awesome. And then equating corresponding components, we will have C1 minus C3 has to be equal to U1, 2C1 plus C2 plus C3 is U2, and then 3C1 plus 2C2 plus C3 equals U3. I just want to let you know right now that we're going to learn an easier way to find out information about spanning via a theorem in this section, and then in chapter 3, I think it's in, is it chapter 3, using determinants. But right now we are going to do it the long way, and I know it's going to look a bit abstract, but that's okay, right? Because linear is abstract, all right? So here we go. You can either do this as a system or in a matrix. Why don't we go ahead and do it in a matrix? So I'm going to come down to this page. I'm going to write this corresponding matrix, all right? So here we go. The C's are the unknowns. I mean, we have an unknown scale, we have unknown constants at the end, but the C1s, we'll put the coefficients to them in the matrix. So we'll have 1, 0, negative 1, and then U1. And next up, beautiful, 2, 1, 1, U2, and 3, 2, 1, U3. Cool, cool. I just wanted to point something out while we're here. Take a look at the vectors above. Do you see that the columns are the same as these row vectors up here? All right, so if you remember that, it can be a lot faster for you to start solving a linear system. Okay, so now let's go ahead. We end up with what? If I do negative 2 row 1 plus row 2, I'll get a new row 2. So rewriting rows 1 and 3, we will have this here, and then we'll do the second row in a different color, the changed row. So here we go. We'll get 0, and then what? 1, 2 plus 1, we would get 3, okay? And then over here, we'll actually need a little more room, I think. What's going to happen? Negative 2 times row 1 would give me a negative 2u1, right? And then I'm adding row 2, so it would be plus u2. Cool so far? Awesome. All right. Well, what next? Good, we need to get rid of that 3 that's in row 3, column 1. So if I go negative 3, row 1, plus row 3 for a new row 3, we will have. I'm rewriting the unchanging rows first. And let's see what our new row 3 is. So this would 0 out, just like our evil plan. We'd have a 2 here. Negative 3 times negative 1 is positive 3, so we get a 4 in the next part. And then we would have a negative 3. Oh, and I'm sorry, I just saw something weird. This should be U1 still. My bad. You see where I made the change? I'm going to do them in that same color so that it doesn't look messy. I'll do them in black so you see that it was a correction. Alrighty, so then we'll get negative 3 U1 and then plus U3 for our new last part of our new row. And what next? What should we do next? Beautiful. We need to get rid of the 2 that's in the third row, second column. So if I say negative 2, row 2, plus row 3 for a new row 3, let's see what we have. So again, rewriting row 1, and then we'll have, what else is not changing, row 2, so we'll have 0, 1, 3, negative 2u1 plus u2, and our new row 3 will be, so we'll still have a 0 here, we'll get a 0 here, just like our evil plan. And then negative 2 times 3 is negative 6, plus 4 would give us a negative 2. And then, okay, negative 2 times negative 2u1 gives us 4u1. And then adding negative 3u1 will give us just u1. Negative 2 times u2 plus 0 u2s gives us minus 2 u2s. And then I'll have the plus u3 still hanging out. Cool, cool. All right, so now what we want to do is we want to, you can either put this, back into the system now, or we can you know what? Let's just get this into Gauss-Jordan, right? Or at least close to Gauss-Jordan, so that we can, it'll be easy for us. So that means we now need to get our 3 zeros in the upper triangle. So let's do it. So to clear out the 3 that's in the second row and third column, we need to do, let's do 3 row 3 plus 2 row 2 for a new row 2. All right, so we'll have 1 0 negative 1 U1, and then the third row will stay the same. And we'll have a new second row. All right, so first component will still be 0, which is great. The next one, it actually, be careful, this middle one changes to 2. And our next one will be 0 by design, as we designed. And then let's look at our last part. So we would have 3U1 minus 4U1 is negative U1. And then negative 6U2 plus 2U2 is minus 4U2. And then we'll have plus 3U3. All right, so our next one, what do we have to do? We need to clear out the negative 1 that's in the first row, third column. So to do so, let's do this. Let's just do negative row 3 plus 2 row 1 for a new row 1. And we will have this matrix. Let's see, the first row will be changing, so we'll have 0, 2, 0. Negative U1 minus 4 U2 plus 3 U3. 0, 0, negative 2, and then we'll have U1 minus 2 U2 plus U3. And let's see what we get for our new first row. Okay, so let's see. We'll end up with 0 plus 2 is 2. Again, be careful. You have a 2 there. And then for this next one, we still have 0. And by design, on the third one, we have 0. And then when we are, so we'll have negative U1 plus 2U1 is positive U1. And then plus 2U2 minus U3. Groovy? All right. And this in turn will give us the system 2C1 is equal to U1 plus 2U2 minus U3. We'll have 2C2 is equal to negative U1 minus 4U2 plus 3U3. And then negative 2C3 will be U1 minus 2U2 plus U3. And then isolating each, we'll get C1 is 1/2 times U1 plus 2U2 minus U3. C2 would be 1/2 times negative U1 minus 4 u2 plus 3 u3. And for C3, we will have negative 1/2 times u1 minus 2u2 plus u3. Cool so far? So I know this looks really weird, but remember, here's where we were at. We were saying that we needed to have our u1, u2, u3, right, be equal to C1 times 1, 2, 3 plus C2 times 0, 1, 2 plus C3 times negative 1, 1, 1. That was our whole plan. Well, we found these values, right? We've got our C1, C2, and C3. So when we kind of put these back in, it's going to be very abstract looking, but this is what will happen. U1, U2, U3 will be equal to and this is times the vector 1, 2, 3, and then I'll just do this kind of vertically. I'll do each vector in a separate line. And then we'll have plus C2, which is 1/2 negative U1 minus 4U2 plus 3U3. And that one was times the vector that terminates in 0, 1, 2. And then we'll have plus negative 1/2 times U1 minus 2U2 plus U3 times the vector that terminates at negative 1, 1, and 1. So this here is our C1. And then our C2 is this expression. And notice they're in terms of U1, U2, and U3, which are real numbers. And then we'll have C3 is all this. So yeah, the short answer is yes, right? This is a spanning set. But sometimes people think, oh gosh, I don't really like how this looks. So, all right, what if we were to, why don't we let u equal to some random vector? 4, 5, 6. How about that? Okay. So what does that mean? That means u1 is 4, u2 is 5, and u3 is 6. Does that make sense? And so what's going to happen? Well, the vector 4, 5, 6 can be written as, so now if you plug in these values, right, into our expressions for C1, C2, and C3, what would happen? So I would get why don't we let u equal to the vector 1, 1, 1, easy numbers to work with, right? Why don't we just let u equal to 1, 1, 1? So what have we found? Well, it turns out that the vector 1, 1, 1, which is some randomly chosen vector in R3, would be equal to what? If I plug in 1 for each of U1, U2, and U3 for each of our expressions C1, C2, and C3, what would go on? So for C1, inside the parens, what would we have? We'd have 1 plus 2 is 3, minus 1 is 2. Okay? So plugging in 1, 1, 1 in for our expression for C1, we get 1/2 times quantity 1 plus 2 minus 1. So we'd have 1/2 times 2. So we would just get 1 times the vector 1, 2, 3. All right, let's solve for C2 now. So if I put in 1, 1, 1 into the expression that we got for C2, the yellow one, what will we have? We'll have -1 minus 4 is -5. -5 plus 3 is what? -2, and -2 times 1/2 is -1. And that'd be times our 0, 1, 2. And plugging in 1, 1, 1 into our expression for C3, we would have 1 minus 2 is -1, plus 1 is 0, and 0 times -1/2 is still 0. So we'd have plus 0 times -1, 1, and 1. So let's see if that works. Remember, this here meant that U1 was 1, U2 was 1, and U3 was 1, by the way. So let's check it out. Does it work? So if I have this vector 1, 1, 1, is it equal to this combination? Well, 1 minus 0 plus 0 is still 1, so that works. Second component, 2 minus 1 is 1, plus 0 is still 1, that works. And then the third component, 3 minus 2 is 1, plus 0 is 1. So that checks out. So really this one, if we wanted to, we would say just 1, 1, 1 is equal to 1, 2, 3 minus 0, 1, 2. And since that other vector is zeroed out, we don't need to represent it here. So this is just looking at a real example, right? Real meaning plugging in numbers for that vector u, right? Just to kind of show you so that you felt more comfortable with all the variable notation, right? But what we found here, right, when we got, this answer here, this told us, hey, yes, this is a spanning set, okay? Because we can represent any one vector in R3 using a linear combination with this relationship. Cool, cool? So, therefore, S equal to the set 1, 2, 3, 0, 1, 2, -1, 1, 1 spans R3. And then I'm gonna just say see below. Cool, cool? All right, so now let's go ahead and officially define the span of a set, okay? So for span of a set, if S is equal to the vectors V1, vector V2, all the way down to vector VK, if that S is a set of vectors in a vector space, capital V, then the span of S is the set of all linear combinations of the vectors in S. So we would say the span of S is equal to the set C1 V1 plus C2 V2 plus plus CK VK. Notice that you'll get a, each scalar times a vector gives us a vector, just like we were working with. And then we have to explain C1 down to CK. So CI belongs to the real numbers for I equal 1, 2, all the way down to K. Okay, the span of S is denoted by, you can either say, like we did before, span at S, or you can plug in what S is. So span of this set of vectors, V1, V2, all the way down to VK. Cool? So when the span of S is equal to your vector space, capital V, it is said that V is spanned by the set. Of vectors. And those are the examples we saw that we worked out. Or that S spans V. So we'll be dealing with span throughout the rest of the course. So I know it's very abstract, but kind of visualize it the very best you can, and you'll get it. You'll get it soon. Let it sink in. Talk about it with your fellow classmates. Okay, next up we have this theorem. And it turns out that the span at S is a subspace of the vector space V. Okay? So what were the rules for showing something as a subspace? Beautiful. You need to have a non-empty subset of your space V, and you need to show closure under awesome addition and scalar multiplication. Cool? Okay, so here we go. Let's set up everything we need, and let's finish the theorem. So if S is equal to the set vector V1, vector V2, all the way down to vector VK, is a set of vectors in a vector space capital V, then the span of S is a subspace of V. Moreover, span of S is the smallest subspace of V that contains S, in the sense that every other subspace of V that contains S must also contain the span of S. Cool? All right, so here we go. Let's set up everything we need, okay? So if we let U equal to this linear combination, C1 V1 plus C2 V2 plus ... plus CK VK, and W, the vector W, can be D1. It's another linear combination of the set S, so just a different scalar. D1 times V1 plus D2 times V2 plus ... plus DK times VK. And these belong to the span of S, where CI and di belong to the real numbers for I equal 1, 2, 3, all the way down to k. Good so far? All right, so we're also going to need a scalar, right? So since we're already using CIs, why don't we make it easy on ourselves, and why don't we just let V be a scalar, or just it'll belong to the real numbers as well. We'll be using the vectors we just named and the scalar b to show closure under addition and then closure under scalar multiplication. The span cannot be empty. All right, so we're just going to state that the span at S is a non-empty subset of our vector space V. Cool. So basically, you wouldn't use an empty set to denote a spanning set because you can't do a linear combination on an empty set. And then the other thing is that the zero vector is in any vector space. And so that's why it is non-empty. All right, a couple of reasons why it's non-empty. And you're going to have your spanning set, since it's a set of vectors that's in the space V, that means it's a subset of V. Groovy? All right, what now? Let's look at the closure, right? So now we're looking at, we stated our conditions here. And also, this is important. We wanted to state that it's a non-empty subset, all right, of our vector space. And then we're going to need to show closure under addition. And we have all of our conditions we need for it. So if I write our vectors like this, so U was equal to C1V1 plus C2V2 plus ... plus CKVK, and I'm going to write W underneath. W was D1V1 plus D2V2 all the way down to DK VK. Groovy? All right, now why don't we add these? Okay, so we're going to add all of these. So everything, this one plus that one. So here we're going to get U plus W. Groovy? And on the right hand side, we'll have C1V1 plus D1 V1 plus C2 V2 plus D2 V2 plus ... plus quantity CK VK plus DK VK. Cool. All right, that's just adding the two sets. Now, let's see what happens. U plus W equal to, remember, I need to have the constants times something else in order for this to work, for it to be the same format. So remember that we can do this, C1 plus D1 times the vector V1 by the distributive property. And this one would be C2 plus D2 times V2 all the way down to CK plus DK times VK. That was because vector addition is distributive. And now, what haven't we shown that? Which is a vector in the space V. Okay, next up, what do we have? Closure under scalar multiplication So we already have the setup for that one. Let's take a look. We called our scalar b, remember? So b times our vector u is equal to b times c1 times v1 plus c2 times v2 all the way down to ck times vk. Well, bringing in the b, we will have b times u is equal to, so we'll have b times c1 times v1 plus b times c2 times v2 plus dot 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 plus b times ck times vk. Cool so far? And then what will happen? B times u will be equal to, I can use the associative property, right? For scalar multiplication, and I'll have bc1 times v1 plus bc2 times v2 plus dot 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 plus bck times vk. And that is because of what? Vectors are associative under, and that's by, using scalar multiplication. And this one I wrote weird. Wasn't vector addition is distributive. That doesn't make sense, right? My bad. This one is because vectors are distributive, and that's under scalar multiplication as well. Groovy? Which is a vector in the span, right? And actually, I think I messed up earlier. I should have said here, instead of that one, I should have said which is a vector in the span of S. Cool. All right, so here we go. Now we wanted to look for the second part of the proof. So this is really kind of part one, right? Was showing the subspace part. So now let's look at this part. Every other subspace of V that contains S must contain the span of S, right? Of V that contains S must contain the span of S. Cool, cool. So here we go. Why don't we let U be another subspace of V? And it's got to contain S. Cool, cool. So let's let U, the vector U, belong to the span of S. But what does that mean? I mean, that means that U would have to equal to what? C1 V1 plus C2 V2 plus dot 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 plus CK VK, where CI belongs to the real numbers for I equal 1, 2, 3, all the way down to K, right? Just for by definition of span, all right? So, thinking about subsets, right? All of those V's are represented, aren't they? I mean, yeah, something could zero out because one of your CIs or more of your CIs could be zero. Even all of your CIs could be zero. But wouldn't you say that VI would belong to U? Because all of the for I equal 1, 2, all the way down to K. It's kind of one of those so easy it's hard things. So anyway, that finishes off the proof for this. We can put our QED on that one. We've shown what is to be shown. Cool, cool? All right, so next up we have another example, example 3. So for example 3, we want to determine whether some set S spans R2. Well, we do it just like we did before in the lead up to these. We have to, let U equal to any vector that's in your vector space V, which happens to be R2. So why don't we let U equal to U1, U2, such that U1 and U2 are elements of the real numbers. Cool so far? So now, well, what do? You've got two vectors in the set S, right? So we want to say, oh, U equals C1 times these vectors. The first one was 1, -1. The second one is 2, 1. So we multiply that to C2, right? And what was U? U was U1, U2. And what will happen? We'll get C1 comma -C1 plus the vector 2C2 comma C2. Making this one happy vector, what's going to happen? We're going to have C1 plus 2C2 for the first component, and then -C1 plus C2 for our second component. Equating corresponding components, we'll have C1 plus 2C2 is equal to U1, and then -C1 plus C2 is equal to U2. Cool, cool. So, putting this into a matrix, what are we going to have? 1, 2, U1, -1, 1, U2. And what do we want to do? We want to get rid of that -1 in the second row, first column. So if we just add row 1 plus row 2 for a new row 2, that'll make it happen. That'll give us 1, 2, U1. And then we'll have for our new row 0, 3, U1 plus U2. So let's see what we have. Let's just go ahead and put this back in the system. So we'll get C1 plus 2C2 is U1. And we have 3C2 is U1 plus U2. That's going to give us that C2 is equal to 1/3 times U1 plus U2. And plugging this in, all this into the C2 in the first equation. So we'll have C1 plus 2 times 1/3 times quantity U1 plus U2. And for C2, that's equal to U1, which will give us C1 plus 2/3 times U1 plus U2 equals U1. Isolating C1, we'll have -2/3 times U1 plus U2 plus U1. And so C1 will equal to, so -2/3 U1 plus U1 would be 1/3 U1, and then minus 2/3 U2. Cool, cool? So what have we found? We found that U1, U2, which is our vector U, is equal to C1 times that first vector we were dealing with initially, which, so we're going to have 1/3 U1 minus 2/3 U2 times the vector 1, -1. And then we got for C2, we would have plus 1/3 times quantity U1 plus U2. All of this times the vector 2, 1. What does that mean? That means yes, because you've written your CIs in terms of U1 and U2 in a way that is consistent. Cool, cool. So our answer, S spans R2. Or you can think of it as the span of S equals R2. Groovy? So now let's go ahead and look at problem B. So here you've got 3 vectors. Again, why don't we let the vector U equal to U1, U2, where U1 and U2 belong to the real numbers. So U1, U2 would equal to C1 times 1, 2 plus C2 times -2, -4 plus C3 times 1/2, 1, and then work it out again. So we would have U1, U2 equals, so when I put this into one happy vector, I'm going to start going a little faster. we would have 1C1 minus 2C2 plus 1/2 C3 for our first component. And our second component would be 2C1 minus 4C2 plus 1C3. Groovy? Equating our components, we come up with the system C1 minus 2C2 plus 1/2 C3 is equal to U1. And then, beautiful, 2C1 minus 4C2 plus C3 is equal to U2. Cool, cool? All right, so now let's see what happens. We're going to end up with what? This time we can do the matrix again. So this is equivalent to the matrix 1, -2, 1/2 U1, and 2, -4, 1 U2. And what would I need to do first? If I want to get rid of the 2 that's in the second row, first column, I want to make that 0. So if I do -2 row 1 plus row 2 for a new row 2, I'll get this matrix here. I'll rewrite row 1 unchanged. And let's see what happens for our new row 2. We'll get a 0 here. We'll end up, with a 0 in the second one. And then we'll end up with what? And we'll also end up with a 0 in the third one. And let's see what happens for our constant column. We'll end up with -2 U1 plus U2. Cool, cool? All right, so this gives us the system C1 minus 2C2 plus 1/2 C3 equals U1. And then it's going to be 0 is equal to -2 U1 plus U2. And doesn't this mean that U2 has to equal to 2 U1? But what is this telling us? I mean, what it's telling us is that U2 is dependent on U1, right? So here, if I was to write the format, of all the possible vectors I would get, do you see that it would consist of U1, 2 U1, and we know that U1 belongs to the real numbers, but if you think about our vectors, what is it going to look like? What do you think? It is an R2, that is true, but what do you notice about it? Good, it's basically going to be all vectors that lie on a specific line, right? And so if we wanted to take a look, if U1 was 0, you'd be at 0, 0, right? What about if U1 was 2? You'd be at 2, 4, right? So you'd have this vector. What if U1 was -1? You'd be, so -1, you'd be at -2 down here. Do you see these are on the same line, right? So, well, so this, it's not a spanning set of R2. S does not span R2. S does span the line in R2, right? Y is equal to 2x. Cool, cool? Let's check out this next one. So again, if we let U equal to U1, U2, where U1 and U2 belong to the real numbers, so U could be any vector in R2. So then what would we do? We'd have U1, U2 would equal to C1 times -1, 2 plus C2 times 2, -1 plus C3 times 1, 1. Cool, cool? All right. Well, again, working a little faster, U1, U2 would be equal to one happy vector of the form -C1 plus 2C2 plus 1C3 for the first component, and then 2C1 minus C2 plus C3 for the second component. Equating corresponding components, we're going to have -C1 plus 2C2 plus C3 has to be U1, and 2C1 minus C2 plus C3 has to be equal to U2. Cool so far? All right, so again, let's put this into a matrix and get some practice. This will be equivalent to the matrix -1, 2, 1, U1. And then 2, -1, 1, U2. And what do we need to do? Beautiful. If we have 2 row 1 plus row 2, for a new row 2, that'll zero out the 2 in row 2, column 1. So row 1 will stay the same. And our new row 2 will be 0. So then we'd have 4 minus 1 is +3. We'd have 2 plus 1 is +3. And then we would have 2U1 plus U2. Cool, cool? All right. So now we want to put this back into a system. I think it'll be a little easier. So here we go. This will be equivalent to the system -C1 plus 2C2 plus C3 equals U1. And then we have 3C2 plus 3C3 is equal to 2U1 plus U2. All right, so continuing this system, we will have, let's start isolating stuff. So if I isolate C1, I will get, with some algebra, positive 2c2 plus c3 minus u1. And if I isolate c2, I will get 2/3 u1 plus 1/3 u2 minus c3. Cool so far? All right. Now, here, let's check this out. Why don't we let c3 equal to t, where t belongs to the real numbers, okay? So what's going to happen? Well, let's work with that. Do you see that c2 would end up being 2/3 u1 plus 1/3 u2 minus t, and then working with c1 is going to be equal to 2 times c2. So c2, remember, is 2/3 u1 plus 1/3 u2 minus t. The next part is plus t in for c3, and then minus u1. So we'll get c1 is equal to 4/3 u1 plus 2/3 u2 minus 2t plus t would just be another plus t, and then minus u1. So we will have, combining the two terms that have u1, we'll get positive 1/3 u1 plus 2/3 u2 plus t. Cool so far? And bringing down our c2, we have what? Beautiful. 2/3 u1 plus 1/3 u2 minus t. So notice that we're able to write c1 and c2, in expressions that have our u1 and u2. So basically u1 and u2 are not multiples of each other. And so we're going to get a spanning set. So basically, when I complete this off, remember that this was our linear combination that we were working with. We had our, I want you guys to be able to follow this, okay? On this is where I was working on our simplifying C1. We had let C3 equal to T. So that's where we got these values, okay? And so writing these in terms of our system, so we have, we had this C1, okay? And this is our simplified C1. We have that C3, which we've done, some scalar. And then we have our C2 is this expression here, and it was over here. So what we got at the end of the day was this. We got that U1, U2 is equal to C1, which is 1/3 U1 plus 2/3 U2 plus T times -1, 2. And then we got what? Ours plus C2, which is 2/3 U1 plus 1/3 U2 minus T times the vector to -1. And then C3, we got to just be T, and that's times the vector 1, 1. So we can say that S spans R2, or the span of S equals R2. So that's the answer to the question at hand. And just so you can kind of check out what we found here, why don't we pick any vector? Pick a vector, any vector. While you're thinking, I will highlight the corresponding stuff. This here was our C2. And this here was our C1. And this was our C3. Let's let U equal to the vector -2, 3, and T equal to 0, because that can be any number. All right, well, what would we have? Our C1 under those conditions would be what? We would get -2/3 plus 6/3 is 4/3 times the vector -1, 2, and then C2. I'm plugging in U1 is -2 and U2 is 3, so we'd have -4/3 plus 3/3 is -1/3, and then T is 0. So -1/3 to -1. Sorry, I did the whole thing. So we would have our U vector, our U being vector negative. That's our U vector. So -2, 3 should equal to this. We just pick that out just to try it. Try it out. If you look at the right-hand side, let's check to see if it matches. So 4/3 times -1 is -4/3. -2/3 is -6/3, and that is indeed -2. And then for the second component, 4/3 times 2 is 8/3, and then plus 1/3 is 9/3. So do you see you get 3? So this checks out. Isn't that groovy? I mean, you can just randomly pick any vector that you want in R2, and it works out. Groovy? Okay, so definition of linear independence and linear dependence. A set of vectors S equal to vector 1, vector 2, all the way down to vector K, in a vector space V is called linearly independent when the vector equation C1 V1 plus C2 V2 plus ... plus CK VK equal to the 0 vector has only the trivial solution. Remember what that was? Beautiful. You get all zeros for the coefficients here. So C1 equals C2 equals ... equals CK equals 0. So you get an n-tuple with zeros for all the components. So if there are also non-trivial solutions, then S is called linearly dependent. Cool? Okay, so testing for linear independence and linear dependence. So if we let S equal to the vector set V1, V2, all the way down to VK, that's a set of vectors. In a vector space V, to determine whether S is linearly independent or linearly dependent, use the following steps. So from the vector equation, C1 V1 plus C2 V2 plus ... plus CK vk equal to the 0 vector, write a system of linear equations in the variables c1, c2, all the way down to ck. Use Gaussian elimination to determine whether the system has a unique solution. If the system has only the trivial solution, C1 is 0, C2 is 0, all the way down to CK is 0, then the set S is linearly independent. If the system has non-trivial solutions, then S is linearly dependent. Cool, cool? Okay, so let's do it. Well, we have this vector set S, and we want to know if it's linearly independent or not. So if you want, this could be like your V1, this vector could be your V2, just to fit it with the definition. So that's our vector set S. And now we need to figure out, okay, if I do C1 times V1 plus C2 times V2 equal to the 0 vector, what do I get for my solution? Well, this will be C1 times 3 negative 6 plus C2 times negative 1, 2. Well, what's the 0 vector in this space? Beautiful. 0, 0, ordered pair. Now, putting this in a system. So on the left-hand side, let's get one happy vector. That'll be 3C1 minus C2, comma, negative 6C1 plus 2C2 equals 0, 0. Well, that'll give me the system 3C1 minus C2 is 0, and negative 6C1 plus 2C2 equals 0. What kind of system of equations is that? Awesome, homogeneous system. So if we work this guy out and we put it into a matrix, we'll have 3, negative 1, 0, and negative 6, 2, 0. And then starting our row operations, if we do 2 row 1 plus row 2 for a new row 2, let's see what we get. We will have 3, negative 1, 0. And our new row 2 will be 0, 0, 0. Huh. All right, well, let's put this bad boy back into a system. You see that we'll have 3C1 minus C2 is 0, and that's it, right? So what does that mean? That means that 3C1 equals C2. Do you see this as a dependent system? It doesn't have a unique solution. It doesn't have the trivial solution, right? How many solutions does it have? Good, infinitely many solutions. So, what does that mean? Beautiful. That means that this is a dependent set of vectors. All right? Linearly dependent. By the way, I think on just about every exam that we have, you will have to ascertain whether or not something is linearly independent. So might as well learn it now. All right. Next up, we've got this one. These are easier to solve, aren't they? Because you just have zeros instead of UIs. So again, if we take a look at this, let's call this vector V1, vector V2 for the second one. And so here C1 times V1 plus C2 times V2 equal to the 0 vector? Well, that'll be C1 times 6, 2, 1 plus C2 times negative 1, 3, 2. What's the 0 vector in this space? Awesome. It's an ordered triple, 0, 0, 0. So, getting one happy vector on the left side, we'll have 6C1 minus C2, comma, 2C1 plus 3C2, and then the third will be C1 plus 2C2. And that vector is equal to the 0 vector. So what does that mean? Well, equating corresponding components, we'll have this system here. 6C1 minus C2 is 0. 2C1 plus 3C2 is 0. And C1 plus 2C2 is 0. So if we go ahead and put this guy in, we'll have a second matrix. I'll edit matrix A. And what are we going to have? We're going to have 1, 2, 3 by 3 again. And we'll have 6, negative 1, 0, 2, 3, 0, 0. And then 1, 2, 0. Quit out of there. And then I'm going to just do second entry, and that'll give me RREFA. And notice what we got. And the RREF form is going to be 1, 0, 0, 0, 1, 0, and 0, 0, 0. And bringing that back into a system, what does that mean? That means that C1 is 0 and C2 is 0. So what do you think about this? Beautiful. S is linearly independent because it got the trivial solution. So linearly independent. Cool, cool. All right, part C. S equals 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 1, 1, and 1, 1, 1, 1. So if this is like our V1, V2, V3, and V4, let's see what we're going to have. So, beautiful. We're going to have C1 times V1 plus C2 times V2 plus C3 times V3 plus C4 times V4, and we set that equal to the 0 vector. Well, writing it out, we'll have C1 times 0, 0, 0, 1 plus C2 times 0, 0, 1, 1 plus C3 times 0, 1, 1, 1 plus C4 times 1, 1, 1, 1. And what's the 0 vector in this space? Awesome. 0, 0, 0, 0. We're in 4 space. Cool, cool? Okay, getting one happy vector on the left side, what are we going to have? Well, we'll have 0C1 plus 0C2 plus 0C3 plus 1C4 is plus 1C4. So we'll have C4 and then 0C1 plus 0C2 plus 1C3 plus 1C4. So then we'll have C3 plus C4. Continuing, what's the next one going to be? 0C1 plus 1C2 plus 1C3 plus 1C4. Cool, cool. So that'll be C2 plus C3 plus C4. And then our next component will be C1 plus C2 plus C3 plus C4. Cool, cool. Equals 0, 0, 0, 0. So let's see. So C4 is 0. The next one we got C3 plus C4 is 0. Then we got C2 plus C3 plus C4 is 0. And then we got C1 plus C2 plus C3 plus C4 is 0. Well, what happens? If C4 is 0, do you see that C3 is going to be 0? And, beautiful, C2 plus 0 equal to 0 means that C2 must be 0. And C1 also has to be 0. So this is the trivial solution. C1 was C2 was C3 was equal to C4, which was 0, which is the trivial solution. So that means that S is linearly, beautiful, independent. All right, so a property of linearly dependent sets. It turns out that a set of vectors, S equal to vector 1, vector 2, all the way down to vector k, where you have at least two vectors, is linearly dependent if and only if at least one of the vectors Vj can be written as a linear combination of the other vectors in S. Cool, cool? So when you have an if and only if proof, you have to go both ways, right? Both directions. So the first direction, we're going to assume linear dependence. Okay, I'll say part 1. Suppose S is linearly dependent. Then there exists scalars, or which are real numbers, which aren't all 0, okay, such that C1 times V1 plus C2 times V2 all the way down to CK times VK is equal to the 0 vector. Cool, cool? And why don't we let C1, I just picked it arbitrarily, let's say that C1 is non-zero, okay? So what are we going to have? We're going to have C1 V1 plus C2 V2 plus ... plus CK VK equal to the 0 vector. But since C1 is not 0, we could isolate V1 and we would have V1 would equal to what? Well, it would be 1 over C1 times negative C2 V2 minus, the next one would be C3 V3 minus ... minus CK VK. Okay, but what is this? V1 is negative C2 over C1 V2 minus C3 over C1 V3 minus minus CK over C1 times VK. And isn't that a linear combination of the vectors in the set? The other vectors in the set S? Cool, cool. Well, part 2, we got to go the other way, the other direction on the proof. So going the other direction, well, we now are assuming that we can write one of the vectors, V1, as a linear combination of the other vectors in the set. So we'd have C2V2 plus C3V3 plus ... all the way down to CKVK. Cool, cool? All right, well, if I get V1 on the other side, right? So basically subtracting V1 from both sides, what's going to happen? Beautiful. I'll get the 0 vector. Actually, I should say adding the negative. All right, so then we would have the 0 vector, right, is equal to C2V2 plus C3V3 plus ... plus CKVK minus V1. Cool, cool? So, what do we have? I mean, since the coefficient of the vector V1 is -1, which is non-zero, right? Non-zero. What does that tell us? Beautiful. S is linearly dependent. All right, so we showed both cases, so we're all done with our proof. We've shown what is to be shown. Okay, so theorem 1.7 is a corollary, all right? So two vectors u and v in a vector space V are linearly independent if and only if one is a scalar multiple. Sorry, I should have had 2 spots. Scalar multiple of the other. Okay? So, example 5. Show that the set is linearly dependent by finding a non-trivial linear combination of vectors in the set whose sum is the 0 vector. Then express one of the vectors in the set as a linear combination of the others. Cool, cool? So, here we go. If we call this first one vector V1 and then vector V2 and vector V3, we want to do all the steps for what? Beautiful. To, find out if it's linearly dependent or independent. Here it told us basically it's dependent, but you use the same method. So that was C1V1 plus C2V2 plus C3V3 is equal to the 0 vector. Plugging in the vectors that we know. The 0 vector for this space would be awesome, 0, 0. So getting one happy vector, do you see we'd have 2c1 minus c2 for our first component, the c3 zeroes out. And then our second component is going to be what? A 4c1 minus 2c2 plus 6c3. And that's equal to 0, 0. So equating corresponding components, we will have 2c1 minus c2 is 0. Make that neater. And then 4c1 minus 2c2 plus 6c3 is 0. Cool, cool. So if we put that into its corresponding matrix, what are we going to have? 2, -1, 0, 0. 4, -2, 6, and 0. And what should we do? Beautiful. Let's do -2, row 1, plus row 2 for a new row 2. And we'll have first row is the same, and our new second row will be -4 plus 4 is 0. 2 plus -2 is going to be 0. And good, we'll still have the 6 here. And let's put this back in our system into it as or write it as a system. That's going to give us 2c1 minus c2 equals 0, and then 6c3 equals 0, which means c3 is 0. Cool, cool. So writing one in terms of the other, we will get that C1 is equal to 1/2 of C2. Cool, cool. So, all right, that tells us that there must be non-trivial solutions, right? Since C1 is written in terms of C2. So writing this as the linear combination, do you see C1 was 1/2 C2, so we'd have 1/2 C2 times the vector 2, 4 plus 1 C2 times the vector -1, -2 plus 0 times 0, 6 equals 0, 0. Good so far? And as you can see, you can plug in numbers for C2 or a number for C2 if you like, but you'll be able to see that you would get this vector 0, 0 on the left side if you simplified. Groovy? Okay, so the next part was, hey, why don't we express one of these vectors in the set as a linear combination of the other vectors in the set? Okay? All right, well, let's see if we can, okay? So we'll do this one in another color. So let's do this one as, let's say we have C1 times our 2, 4 plus C2 times our -1, -2, and let's set that equal to 0, 6 and see if we get something that'll work. Well, making one happy vector, do you see on the left we'd have 2c1 minus c2 for the first component, and then the second component would be 4c1 minus 2c2, and that's going to equal to 0, 6. So then this gives us the system 2c1 minus c2 is 0, and 4c1 minus 2c2 is 6. So putting this into a vector, what do we have? Or a vector, sorry. Putting this into a matrix, we're going to have 2, -1, 0, 4, -2, 6. So then, if I multiply the first row by 2 and add the second row for a new row 2, let's see what happens. We'll have 2, -1, 0 again. And then now our new row 2 will be what? We'll have 0, because we'd have -4 plus 4. And then +2 plus -2 is 0. And then we would have what? 0 plus 6 is 6. And do you see that one is a contradiction? So you can't use that. You can't use that one. Contradiction. So that doesn't work. You can't write 0, 6 using as a linear combination of the other two. All right. So why don't we try something else? So why that would tell us that we're going to have to use different vectors. C1 times -1, -2 plus C2 times 0, 6. And see if we can find C1 and C2 where they'll equal to 2, 4. Okay? So that's going to give us the vector -C1 for our first component, and then -2C1 plus 6C2 for the second component, and that'll equal to 2, 4. This gives us our system. -C1 is 2, and then -2C1 plus 6C2 is 4. Well, if -C1 is 2, that means that C1 is -2. Cool so far? And then over here, if I plug that into that system, I would get -2 times -2 plus 6C2 is 4. And so that would give us that C2 would have to be 0. And so what did we find? We found that, and this is what I plugged in, by the way, we found that C1 was -2, so I plugged that in for this guy. Cool, cool. And then we found C2. So we got that -2 times -1, -2 plus 0 times 0, 6 equals 2, 4. So we've written two of the vectors in the set as a linear, one of the vectors in the set is a linear combination of the other two. Groovy? All right, so this one, just so you know, that one, remember, didn't work. But this guy did. All right, so let's see. Just so you can, the green part was when we expressed one of the vectors in the set as a linear combination of the others. And then this blue part was, we showed that the set was linearly dependent. All right, definition of basis. A set of vectors S equal to vector 1, vector 2, all the way down to vector n in a vector space V is called a basis for V when 1, S spans V, and 2, S is linearly independent. Let's check it out. It turns out that, what we were playing around with before happens to be the standard basis for R3. All right, so just redrawing this really quick. Remember that this was the first vector, 1, 1, 0, 0. And then here we've got 0, 1, 0. And up here we've got 0, 0, 1. And that it turns out that that is the standard basis for our 3. So the standard basis for our 3, S equals 2, 1, 0, 0, 0, 1, 0, 0, 0, 1. Standard basis for R3. So thinking about that, what do you think the standard basis for R2 is? Beautiful. The standard basis for R2 would be 1, 0, 0, 1. What about R5? Awesome. It would be 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, and finally 0, 0, 0, 0, 1. All right, what about for Rn? What do you think for Rn? So you would end up having n vectors, right? And it would look like 1, 0, 0, dot, 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 all the way down to 0. 0, 1, 0, 0, dot, 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 0. We'll do another one. 0, 0, 1, 0, 0, dot, 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 all the way down to 0. And then it would go in that manner until you got to 0, 0, dot, 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 0, 1, 0, and then 0, 0, dot, 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 0, 0, 1. And this would have n vectors, n vectors. All right, so determine whether S is a basis for the indicated vector space. So here, it has to span and it has to be linearly independent. I don't think this is going to span because do you notice that all of the basis sets have the same number of vectors as the dimension we were in R, right? That, by the way, works for R, but not for every other Rn, but not for every other vector space. Well, this is space R3, and we only have 2 vectors, so I don't think it's going to span. I think might be linearly independent, but I don't think it'll span. Here we go. If we let U equal to U1, U2, and U3, such that U1, U2, and U3 belong to the real numbers, then how would we set it up? Remember, you have your U1, U2, U3 is going to equal to C1 times this vector here, 2, 1, 0, plus C2 times 0, negative 1, 1. Cool, cool. Well, we would have u1, u2, and u3, that vector and component form, would be equal to the vector 2c1 for the first component, c1 minus c2 for the second component, and then c2 for the third component. Cool, cool? So we'd get the system 2c1 equals u1, c1 minus c2 is equal to u2, and c2 is equal to u3. Cool so far? So, what would that give us? Well, if C2 is equal to U3, then what would that mean? That would mean that C1 would equal to C2 plus U2, but we said C2 was U3, so C1 would equal to U3 plus U2. Cool, cool? All right. We also have another expression for C1 from the top equation. So the top equation says that C1 would be equal to 1/2 times U1. So when you have this kind of situation, you need to be a little bit careful, okay? Because there could be something hinky going on. So I'm going to check it out, okay? What we got here was this. We got that U1, U2, U3, so any vector in R3 can be written as C1 times the first vector. So we have two expressions for C1, so I'll do it different ways. So 1/2 U1 times 210 plus U3 times 0, -1, 1. That's one thing we got, right? But another thing we got was that U1, U2, U3 is equal to this other expression we got for C1, right? Which was U3 plus U2 times 210 plus U3 times 0, -1, 1. So let's check it out. Why don't we let U equal to 1, 2, 3, okay? So U1 is 1, U2 is 2, and U3 is 3. So does this equal to 1/2 times 1, which is 1/2 times 210, and then U3 was 3, so plus 3 times 0, -1, 1. Well, let's see. This one for sure equals 1/2 times 2 is 1 plus 0. We get the 1. 1/2 times 1 is 1/2. And 1/2 minus 3 is what? Isn't that a -5/2? And then for the last component it would work, but this doesn't work, right? So here it's just not working out, right? So basically what we have going on, if one of them's not going to work out, it's just not going to span. So S does not span R3, right? So for our conclusion, what would we say? We would say that S is not a basis for R3 since S does not span R3. And again, we're going to have a shorter way when we get to determinants to ascertain whether or not something spans. Uniqueness of basis representation. So if S is equal to this set, vector v1, vector v2, all the way down to vector vn, if S is a basis for a vector space V, then every vector in V can be written in one and only one way, as a linear combination of vectors in S. Okay? What does it mean for something to be a basis? Good. It's a linearly independent spanning set. Okay? So, here we go. Since S is a basis, right? That is part of the premise. For V, S spans V, and S is linearly independent. That's by definition a span, or by definition a basis. Cool, cool. So, if we let some vector U equal to a linear combination of the vectors in V, suppose U could also be written differently, right? Call it B1V1 plus B2V2 plus plus BNVN. Also. So again, remember the evil plan here, it says in one and only one way. So what we want to show is that C1 is B1, C2 is B2, etc. Okay? That's the evil plan. So we can write U is equal to C1V1 plus C2V2 plus plus CNVN. And then also U was equal to B1V1 plus B2V2 plus plus BNVN. And let's add the opposite. We're going to add the opposite. So, in other words, kind of subtract. So, what are we going to get? U plus negative U is a zero vector, correct? And that's equal to what? Well, we'd have C1V1 minus B1V1 plus C2V2 minus B2V2 plus plus CNVN minus BNVN. And what can we do? We can rewrite this as C1 minus B1 times V1 plus quantity C2 minus B2 times V2 plus plus Cn minus Bn times Vn. Groovy? So what does that mean? We know that S is linearly independent, right? So what does that tell us? It tells us that C1 minus B1 has to be 0. C2 minus B2 has to be 0. All the way to Cn minus Bn has to be 0. And what does that mean? C1 equals B1. C2 equals B2. All the way down here, you get Cn is equal to Bn. And this part was because S is linearly independent. Cool, cool? So we've done it. Thus, the basis representation is unique. That's what can be written in one and only one way means. Groovy? All right. Here we go. Theorem 1.9, very useful. Bases and linear dependence. If S, the set S, is equal to vector v1, vector v2, all the way down to vector vn, is a basis for a vector space V, then every set containing more than n vectors in V is linearly dependent. Okay? And another useful theorem, the number of vectors in a basis. If a vector space V has one basis with n vectors, then every basis for V has to have n vectors. Very powerful. So the proof for this, let's let S1 equal to V1, V2, all the way down to Vn. And we're going to have this set be a basis for our space V. Suppose S2 equal to U1, U2, all the way down to also be, suppose that also is a basis for V. So the evil plan here is we're going to want to show that n is equal to m, okay? So here we go. Since S1 is linearly independent, and we know that why? Because S1 is a basis, right? Okay. And S2 spans V, and again, that we know because S2 is a basis, all right? Well, since we know that, n has to be less than or equal to m. Cool so far? And that's by what? That last one of those theorems, theorem 1.9. Okay. Similarly, since S2 is linearly independent, and S1 spans V, M has to be less than or equal to N. And that's again using that theorem 1.9. Therefore, M has to equal N, right? Because of the inequality statements. Cool, cool? All right. Definition of dimension of a vector space. So if a vector space V has a basis consisting of n vectors, then the number n is called the dimension of V, denoted by dim V, parentheses V. When V consists of the 0 vector alone, the dimension of V is defined as 0. So in Rn, it's real easy. The dimension of Rn is n, because remember it had n vectors in the basis. Now remember this carefully, okay? This will come back. You figure out the dimension of a space by counting the number of vectors that are in the standard basis. Write that down in capital letters. Cool, cool? All right. So determine the dimension of each of these vector spaces. Well, how many vectors did we have in a standard basis for R2? We had 2, didn't we? So the dimension of our space R2 equals 2. Dimension of our space R5, we did these earlier. Remember earlier example? We had 5 vectors. The dimension of Rn is going to be n because we had n vectors. Cool, cool? All right. Basis tests in an n-dimensional space. So let V be a vector space of dimension n. If S is equal to the set V1, V2, all the way down to Vn, is a linearly independent set of vectors in V, then S is a basis for V. Cool, cool? It also turns out if S equal to V1, V2, all the way down to Vn, and if that set spans V, then S is a basis for V. And the trick here is that if you know the dimension of your space, you can utilize this. So the key to these is that we knew that our vector space was of dimension n. That's how that works out. So let's look at this next example. Determine whether S is a basis for the indicated vector space. Well, personally, since we don't have determinants to use, I think it's easier to find out if something is linearly independent or not. So the dimension of R2 equals 2, and S has 2 vectors. Okay? So if I can show just one of those things, then what? I can show it's a basis. So here we go. I'll find out if it's linearly independent. All right, well, got to do C1 times vector 1, 2 plus C2 times vector 1, negative 1. And we set that equal to the 0 vector for R2, which is 0, 0. So getting one happy vector, we'll have C1 plus C2 for the first component and 2C1 minus C2 for the second component. and that's equal to 0, 0. Setting up our system, we have C1 plus C2 is 0, and 2C1 minus C2 is 0. Well, we can just add these two equations, and we'll get what? 3C1 is equal to 0, so C1 is 0. Well, if C1 is 0, what's going to happen? You'd have 0 plus C2 is 0, so C2 is 0. So I just plugged in 0 for C1 from what I found right there. So C1 equals C2 equals 0. That's the trivial solution. So we found out that S is linearly independent. So putting the concepts together, right, we have two vectors in a two-dimensional space that are linearly independent. So what can we say? Since S is linearly independent, and contains two vectors, and the dimension of our space R2 is equal to 2. Since those things are true, S is a basis for R2, and that's utilizing this theorem here. By theorem 1.11. Cool, cool? So if you remember this theorem, you can utilize this on the first exam, okay? So, that wraps it up for today. I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, please subscribe and tell your friends. Bye.